You can take an entire course including topics in this video through our website and get a certificate of completion from RASOF, the online educational radio frequency institute located in Irvine, California. Instructions and coupon for taking this course is provided at the end of this video. In this section, we are going to discuss about mixer, which is one of the most important blocks that's used inside transmitter and receiver. So what is mixer? It's a 3-port passive or active device that can modulate or demodulate signal. And also we can say it's used for up conversion and down conversion. We are going to talk about this in upcoming slides. The purpose is to change the frequency of electromagnetic signal while preserving every other characteristics such as phase and amplitude. So actually we try to do that, but we know that the phase and especially the amplitude is not constant in mixing. So they change actually, especially when we are having the mismatch between our devices. We will experience this kind of change, but the main purpose here, the main goal is to change the frequency. We use the mixer for up conversion to increase the frequency of the signal, or down conversion, or decrease the frequency from RF to IF or RF to low frequency, and in other words we are doing a frequency shift. So let's talk about up conversion and down conversion. Up conversion happens inside our transmitter, so this is for TX. So imagine that we have a modulated signal here. As you see, this channel shows the spectrum of modulated signal. We will have modulation course, and in that course we are going to explain why we have this kind of spectrum shape, but here is off topic, so we are not going to explain about this. So imagine that this is the modulated signal, and now we are going to send this signal with our transmitter. So we have to do up conversion. It means that we have to increase the frequency and do frequency shift. So we use mixer, and if this is FIF, we mix this with the local oscillator, and local oscillator here has a RF frequency. So this FLO is RF. And at the end of this mixing, we will have this kind of thing. So it means that, as you see, and at the end of the mixing, we will have two channels, and we call them sidebands. And generally, in transmitter, we want to filter them out. We want to have one of them. We don't want both of them, because we are actually wasting our power here. So as you see, in up conversion, we are able to do frequency shift, and we are increasing the frequency from IF to RF. Now we have two frequencies here. So these channels are now around the local oscillator, and these are actually the center frequency of these channels. We are going to explain about this in upcoming slides. Let's talk about down conversion. Now imagine that we have RF signal which is captured by antenna, then we want to decrease the frequency. We want to do frequency shift in order to bring it back to IF or even lower frequencies. And here we will be able to do filtering, amplification, and all the process. But first we have to do this conversion. And here we again have to mix with local oscillator. And we use mixer. So the radio frequency is mixed with local oscillator, and now we can have the lower frequencies here. So this is called down conversion, and this happens inside receiver. It's RX task. So let's calculate and see what is happening inside the mixer. First of all, we have to talk about the carrier. So we said the carrier is actually a signal. It's a cosine signal with a high frequency. So what is carrier? It's cosine 2p AT. A here is a frequency. So we can say this A is equal to F0. F0 is the frequency of local oscillator. So we have the mixer, and we actually use this signal for as our carrier. So this is carrier, and we have our input. It doesn't matter, it can be down conversion or up conversion. So let's say this is input, and we will have something at the output here. So let's see the frequency transform of carrier. It's a cosine wave, so basically we can write this signal system equation, and at the end we can reach this value. And if we say that the frequency of this carrier is F0, and F0 is a RF frequency, so at the output we will have something like this, and this A here we can replace this with F0 and F0 here as well. So what is the output spectrum? We have deltas here as you see, with amplitude of 1/2. So we have deltas here, the one in FO. So we have deltas here. One is on FO and the other one is minus FO. So now let's see what is happening in mixing. So we have the output signal, which is equal to the mix of input. We multiply input by cosine 2pf02. This is our carrier. So this is a cosine 2pf0t. And we have modulated signal at the input of this mixer. Because we have to explain this actually. We have a course about transmitter and receiver. We are going to explain all this there. If you are interested to know about this, we are actually explain all the things in that course in details. But here I'm gonna explain it very briefly. So we always have to modulate our data. We never directly send the data to the mixer. So generally, in most of the structures, we are mixing the modulated data, which has IF frequency. So this after this modulation, our data has a channel, and here we have IF frequency, for example. And here we are trying to upconvert from the IF to RF. So this part we will have RF. So it's very important to know that this part we will have modulated signal. So this input is a modulated signal, and when we go to frequency domain, we can show it like this because modulated signal has also channels. We are going to show in this picture. So this is actually the form we can show the modulated signal in F domain. So this is modulated. And now we are trying to do up conversion. We use our mixer, so we have to multiply this by cosine, and in the Fourier transform, it will change to convolution. And here we found this previously. It's a Fourier transform of cosine. And let's see what we have at the output. So this is our input, okay? And as you see, these are the frequency spectrum of the carrier. So we said this should be FLO, and this should be minus FLO. So generally what we have after modulation is this kind of a spectrum. In modulation course, we are going to explain why we have this kind of spectrums, why the shape is like this. So here it's kind of off topic and we are not going to talk about this in detail. So imagine that this is the input of mixer with the center frequency of FIF, and here we have minus FIF. So this is the modulated signal. Our signal is ready and we are trying to use the mixer in order to down convert. So let's see what's happening at the output. We have exactly 4 components here, as you see, because we have 2 here and 2 here. We have to convolve them all. And let's see what kind of center frequencies we have here. So this is, we can say F minus FLO, IF plus FLO or FO, it doesn't matter. FO is FLO. And here we have F minus FIF minus FO. Here we have F minus FO minus FIF. And for the last one, we will have F minus, so we can write like this, minus FIF plus FO. Something like this. So if we want to find the place of these channels, these are the 4 channels we have after up conversion. You will see the channels are here. So let's see for upper side bands. As you see here, we have something like FLO plus FIF, so it should be this one, the one here. As you see, this is the one. So here we have our channel FLO plus, or FO. I'm just FLO is FO here, FO is FLO. Don't get confused here. And this should be FIF. And here, what kind of thing we have at the center of this channel? It's FLO minus FIF, so it should be this one. This is our second, as you see, channel here. So 1, 2. And this should be FLO minus FIF. So as you see, now we have been able to up convert our channel. This is I frequency. Now at the output of this mixer, we have up conversion, and we have 2 channels here, as you see, the 1 and 2 here. So this is called up conversion, and especially for this part, for the negative part, we are also up converting to this part, and also this one as well. So they are going to the higher frequencies, and as you see, they're really close to FLO. It means that these are higher frequency, and we are successful. We upconverted the channel as we expected before. But generally, we have to know that in books or some pictures, we always show the positive frequency. So we now actually reach the figure that we had previously. Let me show. So if you remember, we said in off-car version we have something like this. As you see, we are upconverting from IF to higher frequencies. Let's talk about an example. Imagine that we have an input of cosine 2p f1. This is our input, and we are this is the output, cosine 2p fct. We are trying to upconvert here. As you see, this is intermediate frequency 100 megahertz and fc is 2 gigahertz. So here, instead of going to the frequency domain, we can use one of the features of cosine. We know from math equations. So we can say cosine a times cosine b is equal to a half of cosine a plus b plus cosine a minus b. So we can write like this here, our a. What is the a here? This is the a, of course. And what is b? The b is the second frequency, the second cosine here. So what should we can write exactly like this. So as you see, what kind of spectrums we have at the output. This is the input. We have f1, the cosine. I'm showing the positive frequency. This is the frequency axis, and this is the carrier. So what we will have at the output, as you see, we have these two cosines. So it means that we will have two deltas, and the center frequency, as you see here, this is the one, f1 plus fc, and this second one is fc minus f1. Let's see what kind of frequencies we have. So here, this one is 100 megahertz. This one is 2 gigahertz. So this part is 2.1 gigahertz. And what about this one? This one will be 1.9 gigahertz. So as you see, initially we had 100 megahertz. Using this mixer, now we upconverted our channel, our data, whatever, to the higher frequencies, and now they are around the local oscillator, and now we can send them, we can connect them to the antenna and send them to the air. Hey guys, thank you for watching the entire video. I'm going to provide you with a coupon for taking RF Fundamental Basic Concepts and Components, RA RF 101. So you can get this course from our website. If you go to the page, you just have to select the buy this course and register here. As you see, if you're not registered up to now. So you need your username, email, password, and also you have to answer a security question. And then you can press the register button, press the sign up button, and you will be able to register in our website. Then after that, all you need to do is going to the course landing page and go to checkout, and as you see, click to enter your code. You can put the coupon code here and then apply the coupon. So then you will have this course for free, and you can take this course. As you see, you won't pay anything for this course. Rasoft has one of the most complete online certificate in radio frequency available, which covers practical topics needed to be a knowledgeable RF engineer. Since all courses are consulted closely by design engineers and pioneers whom have worked as RF engineers in top RF companies such as Qualcomm, Broadcom, Skyworks, Intel, and Apple, as well as avionic companies. It covers the necessary information to land a job or successful in your career. Your first step to take the prerequisite course, RA RF 101, which we have provided the free coupon for it, RFPREREQ 101. See you there shortly.